Hello everyone, my name is Omer and I'm going to talk about our graph-based approach to ad and tracker blocking called AdGraph. I'm from University of Iowa and this is a joint work with our collaborators from the Brave browser, University of California Riverside and Imperial College London. Online advertising allows publishers to monetize their free content and services. According to the Interactive Advertising Bureau, advertising revenue in US alone was more than $100 billion in 2019. While online advertising seems beneficial for publishers, it creates several problems for end users. First, users have privacy concerns about personalized ads that are targeted based on information collected by online trackers. It may seem fine if you're interested in buying shoes and you see an ad about shoes, but it gets really creepy when ads seems to know about things that you don't want them to know. Second, online advertising and tracking paraphernalia seriously degrades page load times. Websites typically embed several ads which take a long time to load. For example, the figure on the right provides a breakdown of page load time for loading ads and actual content for popular news websites. It shows that a lot of time is spent on loading ads as compared to loading actual content. Third, online advertising is often exploited to spread malware. There have been several advertising campaigns that targeted popular websites such as New York Times and BBC. And fourth, ads are intrusive. They interfere with functional content on the websites and degrade user experience. At times, we see websites that are full of ads, and it's difficult to spot what is actually useful on them. Thankfully, we have ad and tracker blocking tools such as AdBlock Plus and Brave that address these problems by getting rid of ads and trackers. In this talk, I will first give an overview of prior approaches and explain why they suffer from scalability and accuracy issues. Then I will talk about our proposed approach AdGraph that addresses these issues. Before I start talking about ad and tracker blocking, let's first discuss what ad and trackers are. Ads are audio-visual promotional content that are displayed on a web page, for example, the image at the right bottom of the screen. Whereas trackers collect sensitive user information like browsing history. In contrast to ads, trackers are mostly hidden from the user view and at times in form of invisible pixels. If you look at them a little technically, both ads and trackers are created by embedded advertising and tracking scripts on websites, which send HTTP requests to load them and use HTML to display them. So collectively, ads and trackers are a combination of HTML, network, and JavaScript layers of the web stack. Now that I have explained at a high level how online advertising and tracking works, let's try to understand how ad and tracker blockers work. The state-of-the-art ad and tracker blocking tools essentially rely on blacklists or filter lists of known ad and trackers. These filter lists are manually created by volunteers based on informal crowdsourcing. It means that people report websites with ads and trackers on filter list forums, and then volunteers create rules to block ads and trackers on those websites. Unfortunately, this manual filter list curation process does not scale well. For example, prior research shows that at times it takes as long as 3 months to add rules for newly discovered ads and trackers. Moreover, once a rule is added to the filter list, it is rarely removed. Even after the ad and tracking domain no longer serves ads and trackers, it takes as long as 4 years to remove unused rules from filter lists. The presence of unused rules leads to staleness. A recent study showed that almost 90% of the rules in filter lists are rarely or never used. These filter lists also suffer from accuracy issues. They operate at HTML, network, or JavaScript layer, but in isolation. They block network requests that load ads. If they are unsuccessful, they try to hide HTML elements that display them. And if they still fail, they try to stop the execution of scripts that aid ad and trackers. Thus, filter lists miss ads at each layer of the blocking, and the final page load ends up having several ads. Overall, filter lists suffer from scalability and accuracy issues. To solve these issues, prior research has proposed to use machine learning for ad and tracker blocking. Unfortunately, these solutions operate either at the network layer or the JavaScript layer. The network layer approaches try to learn the advertising and tracking patterns by featureizing the HTTP request and response headers. They look for the presence of certain identifiers in the HTTP header to predict whether the request is going to load an ad or a tracker. For example, whether the URL has ad-related keywords in them. The JavaScript layer approaches try to learn advertising and tracking by featureizing these scripts. They look for the presence of certain APIs in the scripts to predict whether they are advertising or tracking related. For example, they check whether the scripts interact with the cookies. While these approaches do a good job at solving the scalability issues by automating ad and tracker blocking, but they suffer from accuracy issues since they do not consider all 3 layers of the web stack. Now, for the rest of this talk, I will discuss how AdGraph solves the accuracy and scalability issues in prior approaches. To address both accuracy and scalability issues, AdGraph considers the full cross-layer context and automates ad and tracker blocking using machine learning. The figure here gives an overview of AdGraph. At high level, AdGraph can be divided into two components. The first component is targeted towards solving the accuracy issues by modeling the ad and tracker behavior in a graph-based cross-layer representation. The second component is targeted towards solving the scalability issues by using machine learning to automatically detect ad and tracker behavior. Specifically, we first instrument Chromium to capture cross-layer interaction among HTML, network, and JavaScript layers. We then use the cross-layer interaction and model it in form of a graph. The graph shows how HTML, network, and JavaScript elements interact in a web page. The graph structure is similar to how a web page is represented in a DOM, plus the addition of JavaScript interactions. The focus part also highlights the view that AdGraph gets in comparison to prior approaches, which see unconnected nodes, whereas AdGraph sees a connected graph. After modeling the interaction in form of a graph, we extract distinguishing patterns from it and feed those patterns to train a machine learning classifier. The machine learning classifier then detects which patterns are ad and tracker related and which are functional. For the next few slides, I will focus on graph-based cross-layer representation of ad and tracking behavior. Before I discuss how AdGraph instruments Chromium to capture cross-layer context, I will describe the importance of considering cross-layer context to detect ads and trackers. Consider the example on the right side of your screen. If we try to model the output of the code without considering the interaction, we will see three independent nodes that do not show any intent. But when we consider their interaction, we'll see a JavaScript element initiating a network request and a network request resulting in an HTML element. Overall, the provenance of these actions leads to the intent of the code. We can see something meaningful here. We can see that a script was responsible for initiating a network request that resulted in an iframe. From a vantage point in browser, it is easy to capture interactions among HTML elements and network requests by simply traversing the DOM. However, it is tricky to get interaction with JavaScript. JavaScript interaction is tricky because the browser does not provide any native API to attribute scripts to HTML elements and network requests. Traditionally, people have relied on stack trace to attribute HTML and network events to JavaScript. This approach is used by popular tracker blocking tools such as Privacy Badger and open source measurement frameworks like OpenWPM. The basic idea is to look at stack at different points of interest. For example, if we want to see which script is responsible for creating an HTML element, we can throw the stack trace and traverse it to determine the initiating script. However, stack trace doesn't provide complete information, for example, in case of eval and inline scripts, and it is also available since a script on a web page runs with the same privilege. The other more promising way to get the JavaScript attribution is browser instrumentation. This approach has been used in prior research for web attack forensics. The basic idea is to hook the browser at points of interest and capture events as they happen. Since it requires browser modification, it is much more complete and correct. In AdGraph, we instrument Chromium to capture fine-grained cross-layer context. Specifically, we instrument both rendering and JavaScript engines. We capture all HTML modifications like element creation, insertion, and deletions, network requests originating from HTML elements and scripts, and JavaScript interactions with HTML elements and network requests. After capturing the cross-layer interactions, we model it in form of a graph. This example here shows the graph representation of an example page. The nodes in the graph correspond to HTML elements, network requests, and scripts. The edges show interaction among these nodes, where dotted edges represent the JavaScript attributions. And the number on the nodes correspond to the line number in the example code. We can make two observations from this graph. One, it can be seen that AdGraph captures the detailed interaction from the first to the last line of the web page, and it captures all the JavaScript attribution that were either partially or completely missed by prior approaches. This concludes the graph-based cross-layer representation of ad and tracking behavior, and now I will discuss the use of machine learning to automatically learn ad and tracking behavior. After constructing the graph, we extract distinguishing ad and tracking patterns from the graph and featurize them to feed to a machine learning classifier. We extract two types of features from the graph: structural features and content features. Structural features correspond to graph-specific properties of ads and trackers, like their degree, connectivity, and ancestry information. To give an example of how graph properties for ads and trackers differ from functional content, we show a partial graph of CNN on the right. The red nodes in the graph represent ads and trackers, and the green nodes in the graph represent functional content. It can be seen from the graph that the green nodes are well connected as compared to the red nodes, which have their own scattered cluster. Such representation of node corresponds to the organization of ads and trackers on web pages, which are usually on the sides and do not interact with functional content. Ultimately, having such organization leads to low average degree connectivity. If you look at the graph here, it can be seen that the ads and trackers have low average degree connectivity as compared to the functional content. The second type of features extracted from graph representation are content features. These features capture the node properties, such as the length of the URL or ad and tracking related keywords in the URL. To demonstrate how node properties for ads and trackers differ from functional content, we show an ad and a tracking URL in the red box and a functional URL in the green box. Both of these URLs are from CNN. It can be seen from the ad and tracking URL that ads and trackers have to share many identifiers to track users, for example, the device ID or the client timestamp. Overall, sharing a number of identifiers makes the ad and tracking URLs much longer as compared to the functional ones. The graph here shows that most functional URLs are less than 200 characters, whereas many ad and tracking URLs are longer than that. After extracting the ad and tracking and functional patterns from the graph, we use them to train a machine learning classifier. As a first step, we label the extracted patterns with ground truth. But unfortunately, we do not have a perfect oracle to determine what is an ad and a tracker. The best thing available to us are filter lists, such as EasyList. And despite their inaccuracies, we rely on them to label ads and trackers. However, since we know that they are unreliable, we manually analyze the disagreements between our classifier's detection and filter list to check the validity of our classifier. After labeling the ad and tracking patterns and functional patterns, we train a random forest ensemble classifier that is particularly useful when the ground truth is unreliable. We then evaluate the accuracy of random forest classifier using tenfold cross validation. Overall, we find that AdGraph performs pretty well, achieving an accuracy of more than 95% and a recall of 86 and a precision of 89%. The webpage here demonstrates how AdGraph performs in practice. The webpage on the left is opened in stock Chromium, and you can see several ads on it, whereas the webpage on the right is opened in AdGraph Chromium, and you can see that the AdGraph blocks all the ads. However, as discussed earlier, that our ground truth is imperfect, we manually analyze disagreements between our classifier's detection and the filter list to determine who is right. We find that filter lists often underblock content for which they do not know whether they are ads and trackers. And it can be seen on the web page on the right that AdGraph detects them since it learns the ad and tracking patterns and does not need to rely on domain names. Overall, we find that AdGraph is right 43% of times in discovering new ads and trackers. We also find that filter lists overblock content as well. This happens due to the presence of overly broad rules. For example, filter lists may block all URLs that have an ad keyword in them. It can be seen on the web page on the right side that the filter list block functional content such as the subscription input field, whereas AdGraph only blocks the ads on that page and lets the functional content through. Overall, we find that AdGraph is right 28% of the time in correctly identifying functional content. We find that AdGraph not only has high accuracy, it often corrects mistakes in the filter lists. Next, we evaluate the performance of AdGraph and check its feasibility as a real-time ad and tracker blocker. The performance evaluation is important because our browser instrumentation and classification incur an overhead cost. To estimate the cost of overhead in AdGraph, we compare the page load time of websites in AdGraph versus stock Chromium and AdBlock Plus. By comparing with the stock Chromium, we analyze overhead of machine learning-based ad and tracker blocking, and by comparing it with AdBlock Plus, we analyze its practicality in comparison to a popular ad and tracker blocking tool. Interestingly, we find that AdGraph makes up for the instrumentation and classification overheads by blocking network requests and doing less rendering. In comparison to stock Chromium, we find that AdGraph loads 42% of the websites faster. These are the websites on which AdGraph blocks more content. In comparison to AdBlock Plus, we find that AdGraph loads 78% of the websites faster. We attribute improvements over AdBlock Plus to in-browser ad blocking in contrast to extension layer blocking and avoiding rendering by not relying on HTML element rules. On most websites on which AdGraph is lowered, we find that it only incurs a minor overhead. Overall, we find that AdGraph is not only accurate in blocking ads and trackers, but it also improves the page load time. We have a lot of additional evaluation of AdGraph in the paper, such as the breakage caused by mistakes in the classifier. And I would encourage you to read the paper to see additional evaluation results. Now, before concluding, I will mention some of the takeaways from the talk. I showed that the state-of-the-art ad and tracker blocking tools suffer from accuracy and scalability issues. To address the accuracy issue, we instrumented the browser to capture cross-layer context for effective ad and tracker blocking. To address the scalability issues, we applied machine learning on the cross-layer context to automate ad and tracker blocking. We believe that utility of cross-layer context is not just limited to ad and tracker blocking, it has applications in the other domains. That's why we open source our instrumentation. In fact, AdGraph is now actively maintained by Brave as PageGraph. And we see that it is being used for filter generation for underserved region. With this, I conclude my talk and welcome any questions. Thank you.